All right, so we're in starting into chapter 5, section 5.1, and we are going to talk about how we're going to use identities. And we've talked a little bit about identities and simplifying using identities a little bit. But we're going to go into quite a bit more detail with it in chapter 5 for several reasons. We want to, if we have a complicated trig function, for example, we might want to use identities to help us evaluate this trig function. We might want to use identities to help us simplify an expression. We have a complicated expression. We want to see if we can write it in a simpler way. If there's some kind of quantity that comes up frequently, we say, can we use an identity to write this in a more compact form? So we develop new identities from the ones that we already know. And then one of the big things that we're going to do in chapter 5 is solving trig equations. So we're going to have some kind of application that involves trig equations. So just like the tools that we use for solving algebraic equations, solving for x, we're going to solve for our angle with trig equations, and we use identities to help us out in doing that. So let's review our identities that we've talked about so far, just to talk about the tools that we're going to use. So the first one, we'll talk about the reciprocal identities. So let's remember our reciprocal identities. So cosecant theta equals what? 1 over sine theta. And it goes the other way as well. The sine theta is 1 over cosecant theta. Secant theta, reciprocal of cosine. And it goes the other way around. Cosine theta is the reciprocal of secant theta. And then tangent theta is the reciprocal of what? Cotangent. And that works the other way also. So those are our reciprocal identities. Our quotient identities. Our quotient identities are for tangent theta. And tangent theta as a quotient is sine theta over cosine theta. And then we can write the cotangent theta. We know it's the reciprocal, so we just take the reciprocal of this fraction. So there are our quotient identities. And then the Pythagorean identities. And we said there was one main Pythagorean identity, and the rest really come from that one. So what's our main Pythagorean identity? Sine squared theta plus cosine squared theta, there we go, equals 1. So that's our main Pythagorean identity. We talked about this one we talked about it in a couple of ways, coming from the unit circle. This is the equation of the unit circle, and we talked about it in terms of the Pythagorean theorem. And they're both really the same thing. If we divide everything here by cosine squared, then we get our second Pythagorean identity. We get tangent squared theta plus 1 equals secant squared theta. And then if I divide everything here by sine squared, I get 1 plus cotangent squared theta equals cosecant squared theta. So those are our 3 Pythagorean identities. These we'll use the vast majority of the time when we're working with identities. But there are a few others that will help us out as well. Our cofunction identities. And these had to do with cofunctions and functions of complements. So we said that sine of pi over 2 minus theta was equal to what? Cosine theta. And it works the other way around as well. So the cosine of pi over 2 minus theta equals sine theta. So the cofunctions of the complements equal the function of the original angle. The cosecant of pi over 2 minus theta is equal to what? Secant theta. And it works the other way around. So the secant of pi over 2 minus theta is cosecant theta. This one look familiar? That was on the test yesterday. Which one was on the test? This one. You did it right? Yeah. We talked about this in chapter 4. So we're just kind of remembering the things we talked about in chapter 4. And then our cofunction for tangent and cotangent. So those are our cofunction identities. Cofunctions come up when we're finding the trig function of the complement of an angle. Which? This one? Oh, I got too enthusiastic. All right, and then our last ones that we're going to use for now are even and odd identities. So these are all ones that we've talked about before. We're just kind of gathering them into one place. So the sine function, sine is sine even or odd? Odd. Odd, if we think about the graph, odd functions are symmetric about the origin. What that tells us is the sine of minus theta is minus sine theta. And then the cofunctions are the same. So cosecant would be odd as well. How about the cosine? Was cosine even or odd? Cosine is even, symmetric about the y-axis. So that tells us that cosine of minus theta equals the cosine of theta. How about tangent? Even or odd? Odd. Tangent is odd. If you can't remember, think about the graph of the tangent function, symmetric about the origin. So this means that tangent of minus theta is minus tangent theta. And the cofunctions are the same. So secant would be even, and cotangent would be odd. So cosine and secant are the only two even functions. So we're going to use these to simplify for this first. In this first section, we're going to simplify expressions. So what I want to do is go through several examples of showing you some of these techniques. We'll end up using a lot of techniques, just like we use to simplify algebraic expressions. A lot of techniques that we need to practice with to work with these things. So let's look at some examples. Questions on any of these identities? None of these should be a surprise at this point. Okay. So let's find if cosecant theta is minus 5/3 and cosine theta is greater than 0. We want to find cosine theta using identities. So before we use identities to do this, how would we have done this before? Draw a triangle. These are the two sides of a right triangle, and we would draw a triangle. So we had a problem or two like this on our test history. Well, we want to use identities. Well, I'm going to rewrite cosecant theta as I'm going to use my reciprocal identity and say sine theta equals what here? Someone said it, negative 3/5. And I know my Pythagorean identity says that sine squared theta minus 3/5 squared plus cosine squared theta equals 1. So I get that the cosine squared of theta is 1 minus 9/25. 1 minus 9/25 is what? 16/25. So cosine theta, take the square root of both sides, is 4/5. This process is essentially the same thing that we would do if we drew the right triangle and found the third side of the triangle. Same idea, because this identity comes from the Pythagorean theorem. Just another way to solve this problem using identities. So questions on that example? I need to subtract these two. I need a common denominator, and one is 25/25. So 25 minus 9 is 16. All right, so let's look at another one. A little more complicated this time. We want to simplify. Simplify. We did a few of these. These are the ones that we do in this chapter are going to be a little more complicated. Cosecant squared x, cotangent x, minus cotangent x. All right, so before we do this problem, let me remind us the techniques we would use to simplify an algebraic expression. We might rewrite something. So we might rearrange it. We might group it differently. We might add or subtract. That might involve common denominators. We might use substitution. We know that two things are equal. We can substitute. And we might use factoring. And with trig functions, we can also use identities. So we might use any or all of those techniques in a single problem. So if I want to simplify this, what anybody see how we might want to start this? So we might want to get it out of cosecants and cotangents. So that's a good thing to think about. I'm going to say eventually, but as a first step. Andrew had an idea. What do you think, Zachy? So this, we might turn it into sines and cosines. So that might be involved. What did you think, Joe? Okay. So we might end up doing something like that. So before we start doing that, I want to do the most obvious thing here first. And what was your suggestion, Andrew?
Factor out a cotangent.
Let's factor first. We have a common term of cotangent. So let's factor. So this equals cotangent x times cosecant squared x minus 1. Oh, now I'm happy, because when I see a trig function squared and a 1, what should I think of? Pythagorean identity. So what does the Pythagorean identity tell us about cosecant squared x minus 1? Let's go back here. Cosecant squared, if I subtract 1 from both sides, I'm just left with cotangent squared. So cosecant squared minus 1 is, this equals cotangent x times cotangent squared x, and this simplifies to cotangent cubed x. If I go back to my Pythagorean identity, if I subtract 1 from both sides, I get cosecant squared minus 1 on this side and cotangent squared on that side. So cosecant squared theta minus 1 equals cotangent squared. Okay? So this simplifies to cotangent third of x, which is much easier to work with than this. Yes?
Why is it the x lower?
Cosecant
Like on the last step.
here?
Yeah.
No, so cosecant squared x is the same as cosecant x squared. We're just squaring, we're not squaring the x, we're squaring the function.
Okay.
So the squaring just goes to the function. The x is inside the function. So we're not squaring the x, we're just squaring the function. Okay? Let's look at another one. We want to simplify this one. Tangent x, sine x, plus cosine x. All right, this one, we don't have a common factor here, so factoring doesn't work. So what I'm going to do here is I'm going to write tangent in terms of sines and cosines. So this equals tangent x is sine x over cosine x times sine x plus cosine x. When I multiply these two, I get sine squared x over cosine x plus cosine x. Now I want to add these two. What do I need to do to add these two things? We need a common denominator. Our common denominator is going to be cosine x. So I'm going to multiply this side, this term, by cosine x over cosine x to get my common denominator. I'm getting happy already because this gives me sine squared x plus cosine squared x over our common denominator of cosine x. Sine squared x plus cosine squared x is 1. This is 1 over cosine x, which is secant x. Rather than writing this, it's the same as secant x. Isn't that nifty? Yes. So the question the question was, could I just divide this? You're saying divide everything by cosine? Because I just have an expression, I can't, I'm not divide. You could do that if you were dividing both sides, but I don't have another side here. So everything that I have to do has to make it so it doesn't really change it. And this is cosine x over cosine x is 1, so it doesn't really change it. Okay? All right. Let's look at one that's a little more complicated. Secant x. We're still simplifying. All right, we want to simplify this thing. I'm going to move this over. So we need to subtract these two fractions. What do we need to do to subtract these two fractions? We need a common denominator. So I need to multiply this one by what to get my common denominator? Well, before I say it that way, what is our common denominator? What's our common denominator going to be? 1 plus secant x times tangent x. These two things multiplied together. So I need to multiply this side by secant x over 1 plus secant x. And I need to multiply this side by tangent x over tangent x. And I'm going to do this to remind myself to distribute properly. All right. So on the numerator, in the numerator, what do I end up with here? Someone multiply this out. Tell me what I get.
Secant squared x.
Okay, secant x plus secant squared x. And here?
Tangent squared x.
And I get a minus. Over my common denominator, I'm going to leave it written as 1 plus secant x times tangent x. All right. Anybody see what we're going to do here? Anything in the numerator look like it could be helpful? Let me do this. Don't we have an identity that relates tangent squared and secant squared?
That equals 1.
This gives us 1 because tangent squared x plus 1 equals secant squared x. So if I subtract tangent squared x from both sides, I just get 1. So this is the same as secant x plus 1 over, I'm going to secant x plus 1 times tangent x. What can I do with those secant x's plus 1s? Cancel. So this is 1 over tangent x, which is just cotangent x. So this original thing simplifies to cotangent of x. Isn't that's just such a cool thing. I love doing this. Sometimes working with trig identities is like solving puzzles. It's just you kind of do this and you try this and you try this piece here and see if that piece works there until you get to something that's going to give you an answer. All right, questions on that example? So recognizing these combinations is really important. When you see a trig function squared, look for those Pythagorean identities. Look for some combination, some variation on this Pythagorean identity when you see a trig function squared. That's a hint for you. All right, let's look at a different type of example. For these, we want to factor. So let's start with cosine squared x minus 1. So we want to factor this. We're not simplifying, we're factoring. How are we going to factor this?
Cosine plus 1.
Cosine x plus 1? Cosine x minus 1. This is just like factoring x squared minus 1, but instead of x's, I have cosines. And the way we'll use this technique now is if we had this like we do when we had quadratic functions, cosine squared x minus 1 equals 0. Now I can say cosine x plus 1 equals 0 and cosine x minus 1 equals 0 and come up with solutions. So that's how we're going to apply this. Let's look at another one. Sine squared x minus 3 sine x minus 10. We want to factor that. So how are we going to factor this one? Sine x minus minus 5 sine x plus 2. So we're going to factor this one just like we would factor x squared minus 3x minus 10. But instead of x's, we have sine x. And then if we needed to do something else with these factors, we could. All right, let's look at one that's a little more complicated. Questions on these two before we go on? So we're factoring them just like we factor algebraic expressions. All right, secant squared t minus tangent t minus 3. I want to factor that thing. What's the problem here? I have two different trig functions. But what does this secant squared suggest that we should look at? When we have a trig function squared, we should think of Pythagorean identities. So secant squared t is equal to tangent squared plus 1. So this is tangent squared t plus 1 minus tangent t minus 3. Now I'm going to combine like terms and I get tangent squared t minus tangent t minus 2. And now how can I factor this thing? I know it's going to be a tangent t and a tangent t. And what do you think exactly? Minus 2 and plus 1? And there's my factors. There's this quantity factor. So we had to use an identity before we could factor on this particular one. So this technique is and it comes up quite a bit when we solve trig equations. All right, questions on this process? Okay, let's look at another technique. We want to rewrite 1 over secant x minus 1 so it's not a fraction. So we want this not to be a fraction. For this kind of problem, this one's the idea here is a little trickier. I think of this as doing the same thing when we divide by a complex number. It's kind of like multiplying by the conjugate. So I'm going to multiply the numerator and denominator by secant x plus 1. So it's kind of like we did when we divided by a complex number. Now when I multiply this out, I get on the numerator secant x plus 1. And what do I have in the denominator now? Secant squared x minus 1. Secant squared x minus 1 is tangent squared. This is a Pythagorean identity. Alright, so now we have a less complicated thing in our denominator, but we still have a fraction. Anybody have an idea of what we can do here? So here's another little place. This is a little different than maybe something that we've done a lot in the past. I'm going to split this into two fractions. So basically I'm undoing the adding of the fractions. So this equals secant x over tangent squared x plus 1 over tangent squared x. So I've split this into two fractions with the same denominator. Well, now I can rewrite this as not a fraction, right? I'm going to go over here now. So this is secant x, darn it, over tangent squared x plus cotangent squared x. So now I've gotten rid of one fraction. Well, what can I do with this tangent squared now? One over cotangent, or could I write this as sines and cosines? Yeah? So this equals secant x times sine squared x over cosine squared x. And the reason that I thought of doing this as sines and cosines is because I have a secant x here, and I thought maybe I'll get one of those cosines to cancel. Now what do I do when I divide by a fraction? Multiply by the reciprocal. So this is secant x times cosine squared x over sine squared x plus cotangent squared x. Now we're almost done. What is secant x? How can I rewrite that? 1 over cosine x times cosine squared x over sine squared x plus cotangent squared x. One of these cosines cancels. In the numerator and denominator, so I get cosine x over sine squared x plus cotangent squared x. And how can I rewrite 1 over sine squared x? Cosecant squared. So this is cosine x cosecant squared x plus cotangent squared x. I forgot my x here. So now I've rewritten that so it is not a fraction. Took a fair amount of work, but it's not a fraction now. But this all comes from using our identities, manipulating our identities. Yes? Yes. This one's squared and there's only a 1 there. All right, yes?
So that step exactly why can we use maybe that cotangent squared x, and then go to secant x, and then it's...
So Jake asked from here, from this step, the question was from this step, could I just write this as, I'm going to go over here, as secant x times cotangent squared x plus cotangent squared x. That would be fine. So these two things are equivalent. And this one's probably more useful because now if I wanted to I could factor out that cotangent squared x. So nice observation. All right, let's look at one last thing and then we're done. I just wanted to show you a variety of techniques, go through several of these problems. All right. For this one, we are going to use the substitution. X equals 3 sine u to write the square root of 9 minus x squared as a function of u. So we call this, I mentioned this before when we were drawing our triangles, this is a form of trig substitution. Alright, so I'm just going to plug 3 sine u in here for x. So I'm going to write square root of 9 minus 3 sine u squared. So I get the square root of 9 minus, how would I rewrite, if I square all of this, what do I get? 9 sine squared u. Alright, we should be getting happy already because of the sine squared. What can I do with this now? How can I simplify this? Can I subtract 9 minus 9? No? What can I do with that 9? I can factor it. And 1 minus sine squared u is, what is it? Cosine squared u. This is our Pythagorean identity. The square root of 9 cosine squared u is 3 cosine u. So if x equals 3 sine u, the square root of 9 minus x squared equals 3 cosine u. And that's our answer. We've rewritten this as a function of u. All right, so I've shown you several techniques, several ways of working with these equations. When you're working with these identities, it's not something that is necessarily going to come after trying a couple. It might take a fair amount of work in order to start getting a little bit of intuition and a little bit of familiarity with how we work with these. So the idea is practice, try something. If it doesn't work, try something else. I see these as a puzzle. And when I get to a dead end, that just tells me, okay, that part doesn't work, let me try something else. Okay. There you go.